just gonna trust that everything is working fine because there's nothing else I can do. So I think we can start. This week is going to be about probability, which is one of the more common types of problems you'll see on the AIMC 10. And probability is basically just, you can think of it as the chance of something happening. And I like to define it as the number of desired outcomes of the number of total outcomes. And what I mean by that is you basically just find out how many ways the event that you want to take the probability of can happen, and you divide it by the number of total ways that the number of total events that can happen. For example, if you're rolling a die, and you want the probability of a 1, there's only one way for you to roll a 1, and there are 6 different rolls you can have. So the probability is just 1/6, and that is just the basic concept of probability. Yes. Okay. Do you have a question or comment, concern, anything?
No.
Oh, okay then. Give me a minute. Okay, moving on. Generally speaking, these problems are quite straightforward, and you just have to be careful about not messing up your counting or your understanding of what they're asking for. And a lot of times they're going to be trap answer choices that may seem right but really aren't. One of these is, like, generally speaking, 1/2 is usually not the right answer for a lot of these problems, although take it with a grain of salt because sometimes it is, but most times not. Anyway, a few things you need to know before you do most probability problems is just sort of basic counting concepts. And what I mean by that is orderings. So the number of permutations of an object is n factorial. And what I mean by permutation is the number of ways you can put the objects in order, as in if you have the numbers 1 through n, and you want to put them into, like, I don't know, boxes in a row, then there are n ways to order these numbers, if that makes sense. We'll also go into this when we do the problem, so it's fine if you don't completely understand for now. And it's n factorial, it's just n times n minus 1 times n minus 2 times all the way to 1. And this is intuitive because you can think of it as the first slot having n numbers you can choose from, and the second one will have n minus 1 numbers, and so on until you're left with 1, etc. And the other thing are combinations, and I can't really type it, but it's usually written something like this: n choose k, and n has to be greater than or equal to k. If n is less than k, then it's equal to 0. And what this refers to is the number of ways to choose k objects out of n total objects. And for example, if we want to choose 3 integers, this is going to be probability, but counting is seen in some probability problems. This is why I want to go over it like this a little bit. And basically choosing k objects out of n total objects. So if we're told that we want to choose 2 numbers, two distinct numbers, such that they are between 1 and 10 inclusive, then this is going to be equal to 10 choose 2, and that's actually just 10 times, and this is actually going to be equal to 45, but this is just referring to what this refers to, and the formula itself is going to be n factorial over k factorial times n minus k factorial. And basically what this means is that we want to choose k distinct objects out of these n, right? And the way we do that is, well, this. And basically the concept behind this is that the way we count, the way we choose k objects out of these n is the first one we choose has n ways, and the second one is n minus 1, and so on until we have times n minus, I believe this should be k minus 1. And this is going to be these number of ways to just take k objects in order. But then we have to divide by k factorial for when, because we can take all these objects out. Yeah, because we can just take all these objects out in different orders and they'd still refer to the same group of distinct objects. So this top part right here is n factorial over n minus k factorial, and this bottom part is just k factorial. So then we divide, we're just left with this. Yeah, that's sort of how this works. But again, I'll go into it later, so don't worry too much. And for this one, I didn't like put in too many notes, as I think that the best way to learn about probably just to work with different problems in it and learn the methods that way. So I think I've compiled a few of the more common types of problems you'll see. So yeah, the first case I want to go over is called casework, and basically this is you'll basically split the problem into different cases, and you count the number of ways, or you count the probability of the thing you want occurring in each case, and then you combine them. This is sort of like brute force, but it's more of a systematic brute force approach. So basically, give an example problem. You flip a fair coin 5 times. What is the probability that you never flip 2 heads in a row? And we can use casework in this problem by basically using casework on the number of heads or tails flipped, right? So our first case would be that you have 0 heads, and there's only one way that this can happen, where everything is just tails. You have 1 head, and this can happen 5 ways if you flip the head first, second, third, fourth, or fifth. I'm not going to write them all down, but this is basically what it is. Yes, if you notice, this is actually just 5 choose 1. And another case is 2 heads. And this is where we actually sort of have to be careful, because we can't flip 2 heads in a row. So I think since the numbers are sort of small here, you can straight up just list out all the possible ways this can happen. So from here, we can actually divide this into 2 more cases to help us count it, where we have if it starts with a head or it starts with a tail, the very first flip. The first flip is heads, then we can have heads, then the next one has to be tails, and we're left with 3 spots, and 1 of them is a head and 2 of them are tails. If you notice that the head can be anywhere because it will never be next to the first head. There's 2 ways that this can happen. And then the second case is when we start with tails. And when we start with tails, like again, we can either have a second tails or another head. At this point, you could probably just list them out as if the second one is heads, then the next one has to be tails. Then we're left with either tail head or head tail. And this is just 2. And then if we have 2 tails in the front, then we can only be followed by a head tails head. That's 1. This is 6. And finally, our last case is when we flip 3 heads, and what happens here is that there's only one possible way: heads, tails, heads, tails, heads. This is 1. So in total, if we follow at least, is 1 plus 5 plus 6 plus 1, all divided by the number of, from here, number of desired outcomes over number of total outcomes. Desired outcomes is 1, 5, 6, 1. So this is going to be 13. And the number of total outcomes is going to be 2 to the 5th, as each flip can be heads or tails. So the probability is 13 over 32. It's important to note here that each of these cases, they all have an equal chance of happening, which is why we can just straight up add 1, 5, 6, and 1. And this only works because it is a fair coin. So yeah. Complementary counting is not necessarily better, and I'll explain that later. But funny thing is, complementary is our next method, and this refers to counting the opposite of what we want and then just subtracting that from 1. Let's do this problem first. So my exemplary problem for complementary counting is, let's say we have people A, B, C, D, and E. They're people, and they just have letters as names. How many ways can they sit such that A and B do not sit next to each other? So you could do casework on where A and B sit, and that actually is not a bad method, but an easier method would just be to count the total number of ways that they can sit, which is 5 factorial, as from here, 5 factorial. And then we can subtract the cases where A and B are sitting next to each other, and then divide by 5 factorial again. So in this kind of problem, we can just consider A, B as a block or just one person. So then we're just going to be left with 4 people, the block A, B, C, D, and E. So now we're just left with 4 people, and we will be ordered and divided. So we're just left with 4 factorial. And we also know that A and B, they can be switched, so BA leads to the same result. So this means that we're going to have 48 cases in which A and B sit next to each other. So 5 factorial minus 48 is going to be equal to 72 ways in which they do not sit next to each other. This is actually counting problem. I forgot to make the probability, but after you can just divide by 120. So yeah, this is the gist of a complementary counting problem. And going back to here, it was suggested that you could use complementary counting in this problem, and that is true. You could find the number of ways that you have 2 heads in a row, but what makes it so difficult is that you have to use cases where you have 3 heads in a row, and you can have a lot of overcounting when you consider a case like this. And you're going to have to be able to account for counting these 2 heads and these 2 heads and just in one, or you can count like a certain arrangement multiple times because these heads are in different places, but they're connected. So yeah, that's why I would not recommend complementary counting for this problem. It is more messy than just counting straightforward. But yeah, you'll see that this is a very, very common tip, and it's not just for an ordering problem. And the next one I want to talk about is called geometric probability. And this is honestly one of my favorite ones, as it's pretty rare, but it's really easy to identify. And usually it has 2 variables of some sort, and they are usually bounded in an interval, and they need to satisfy some kind of relationship. And you solve this by graphing it and taking a ratio of areas of points that work over the total number of points that can be. And a great example of this is this problem. So we have A and B are are two real numbers between 0 and 1. And we want to find the probability that the absolute difference between these two numbers is less than 1/2. So basically, if we let the numbers be x and y, we have x and y are between 0 and 1. And we also have x minus y. X minus y is less than 1/2. You can try to do it on your own right now if that's what you want. I mean, or, okay, how about this? I'll give you guys a minute to think about this problem, and yeah, if you think you have a solution in about a minute, then you can raise your hand and we can go over this together. So yeah, but yeah, just think about the gist of the method and how you would be able to apply it to this kind of problem. Okay, well, that is not the yes, that was me. Okay, well, someone has the right answer, and I'll call on them to share.
Can you guys hear me?
Yes.
I can't quite annotate, but what I can just tell them what I did. So just like we can use like the fact of number lines and like how number lines. So if we have a number line from 0 to 1, could you draw like a number line?
Okay.
And like so, there's basically like you can choose a point anywhere from here. Like, you can't go over half. So you're the probability that So all right, okay. So what I would do here is if you pick a number that's greater than half, if a is greater than half, then
Okay.
there's like wait, I have a question. Is the absolute value have to be right? Because if b minus a is
For example, if b is here, then this still works because the difference is still less than 1/2 here. And
so what
absolute base just means distance.
oh all right, okay, there's a better way, then never mind. So what you can do is just make like a coordinate plane and both the area is 1, so you know the denominator yeah, if you make a coordinate plane and then so you have to do a minus b is greater than 1/2. I mean, a minus b is less than 1/2, and you can like I guess graph the equation.
Yeah.
So when
And
you graph,
I'm gonna change it to x and y because it's easier to.
so we want everything that's less than. So first, let's try graphing whatever it's equal to, and then we'll just like shade everything that's lower. So y is equal to x minus 1/2. Yeah. So
Yeah.
basically now what you do is okay, we can use so if you draw like a line between the square, like make it half.
Like this.
No, I meant like straight up, like halfway.
Vertical or horizontal?
Horizontal.
Be like this.
All right, so you can tell that it's half of a half, basically.
Yeah. So this area is wait. Actually, no. What area is half of a half? or whatever you're saying.
The one that's below it, right? Because it's half of a half. No, it's half of a half of a half.
Yes, an easy way you could think about it is just, this length is 1/2 and this length is 1/2 from this equation. So the area is just 1/8. Yeah, this 1/8.
All right, yeah. Thank you for letting me do it.
You didn't solve the problem, but you somehow had you gave me the right answer, but you didn't finish the solution to this problem at least. So I think I'll just take it from here. First, or secondly, from this absolute value thing, we have another equation. And first we have x minus y is less than 1/2. We also have y minus x is greater than 1/2, is not greater than. Y minus x is less than 1/2 is also an equation you need to consider. So we also have to graph y is less than x plus 1/2. And when we graph that, which is going to look like this, and this is points 1/2, this point is also 1/2. So this is our graph, and basically we want to find the area of the region that works. So here we look at the signs of, well, not the signs, but here we look at the inequality signs, and greater than refers to the part of the plane above the line, and less than will refer to the part of the plane below the line. So when we combine the two, this is just this middle section right here. And you can basically just find the area of this section by taking the area of the square and subtracting off these two triangles. It was mentioned before that each of the triangles have area 1/8. This middle section has area of 3/4. And basically, now all we need to do is find the ratio of the areas of the parts that work and the part that doesn't. The part that works is in the middle here, which is 3/4, and the total is just the unit square 1. So our probability is just 3/4 divided by 1, which is 3/4. I do want to go over why this is the case. And you basically need to understand that you need to understand what this graph itself represents. And this is like, if you think about the points or the possible ordered pairs x, y, the unit square where the unit square between 0, 1, like this, every single point inside of this square will satisfy that the x and y are between 0 and 1, and it will also cover every single possible case or every single possible pair that you can get if you choose two numbers between 0 and 1 for both x and y. And after that, when we graph, we can identify the portions of the shape, which are really just a set of a lot of points that will work. And we know that we can just count the distributions, or no, since we know that the points are equally distributed, and that's because, well, we're thinking about all the points really, we can simply just find the area, which you can think of as proportional to the number of points that work, and you divide by the whole area, which is just the total number of points that you can have. So in a sense, it's still using the definition of number desired over number total. And yeah. I use scratchwork.io for this whiteboard in case you were wondering. Although. Okay. But yeah, if you have any questions on this, now would be a good time to ask them. But this is a very powerful method, and if you think about it, if we didn't use geometric probability for this question, I'm not really sure you'd have a really great rigorous way to actually solve it. So yeah, cool problem. And the last type I want to talk about is infinite geometric series, or I think a better name, or what's slightly different would be a recursion problem. And well, in this specific case, in the challenge problems at least, it'll be a game between two people, and each with a certain probability to win on each term. But it can actually be a lot more things, and I'll give an example later. But first, I just want to talk about the geometric series formula. And in case you didn't know, geometric series is basically just a sequence of terms with a starting term A and a common ratio R, and you get the next term by multiplying R by multiplying by R to the previous term. For example, geometric series would be like 1, 2, 4, 8, 16, etc., where A is 1 and R is 2. And basically, this formula says is that if we have a geometric series with first term A and the common difference or common ratio R, then we can find the sum as it approaches infinity is equal to A over 1 minus R. If R is the absolute value of R is less than 1, and it only works if the absolute value of R is less than 1, because if R is greater than 1, then this sequence is just going to get larger and larger, and will go to infinity instead. So, and basically the way you can show this cool thing, if we let S equal to the sum of A plus AR squared, we can multiply by R, so you have SR equals to AR plus AR squared all the way to infinity. And we can subtract, so you have S times 1 minus R just equal to A, so S equals to A over 1 minus R. And this works because you can just sort of abuse the fact that the sequences just trail off to infinity and everything cancels out. So yeah, cool thing. Anyway, so if we go back to the problem, basically, we have two people who are playing a game with a weighted coin that comes up with heads with probability 5/8. And this first person wins if they flip heads, and the second person wins if they flip tails on their turn. And they each take turns flipping the coin until one of them wins. So if A flips tails, then B does not win. It's just B's turn to flip. So what is the probability that B wins the game? And the way you can do this problem is by creating an infinite geometric series and then just finding the sum. So the probability that B wins. So this is okay. The way you approach this problem is you can sort of think of it as infinite casework that will eventually lead to geometric series. And by infinite casework, I mean you can do casework on the number of turns it takes for B to win the game. For example, if B wins the game on its first turn, that happens with probability of 3/8 times 3/8, as there's 3/8 probability A rolls tails, and then a 3/8 that B gets tails, flips tails. And then if B wins on the second turn, then that's going to be 3/5, 3/8 times 5/8, and times 3/8 times 3/8 again. And basically, it's probability A does not win, probability B does not win, probability A does not win again, probability that B wins. And you can see that this pattern holds for each case. And in theory, since it can take an infinite amount of turns to win the game, the sequence will just go off to infinity. But we know that the common ratio between each of these terms is just going to be 3/8 times 5/8. As you can see here, there's an extra one. So we have the A is just equal to 9 over 64, and R is equal to 15 over 64. So the probability is just A over 1 minus R, which is just equal to 9 over 49. And that's probably if B wins. So we basically just can generalize an entire sequence into just one term. And I think that if you don't completely want to go over this, then another method you could use, which is more in line with the name recursion, is we can, okay, method 2. recursion. If we let the probability of B winning equals to P, then we can define P as, well, the probability that B wins the first round, and then, which is 9/64, plus the probability that no one wins in the first round times the probability that you win. And this actually might be a more simple method. And what happens here is that we just get 49/64. P equals to 9/64. And P is just 9/49. However, we still need to understand why this method works and why it's so powerful. And basically, you should read my bio if you have questions. Yes. Basically, the inspiration behind this is, if you notice that what happens what happens after one round does not affect any of the later rounds besides ending. So each turn is, or each round where A goes and B goes is independent of the next round where A goes and B goes. So we can just use the fact that it can go on to infinity. And yeah. I don't know if I explained that clearly, but basically there's 9/64 chance he wins the first round, and then there's a 15/64 chance that no one wins in the first round. And then when we go on to the second round, the probability of him winning is going to be the same as the probability of him winning before the first round even happened. So yeah, that's how it works. And actually, and I just want you to realize that if you go back to the geometric series stuff that I just did, basically this is, if we let P equal to this sequence, then you'll actually find that this is similar to the way you actually prove this equation. Just a cool thing to note, but I'll move on now. Anyway, general tips. Yeah, general tips. Identify the method that you want to use, and if you can't find it, then just try to count it directly. And the probability of an event is always 1 minus the inverse of that event. This is just complementary counting. Don't overthink it, but also check your work. And you can also exploit symmetry, which I'll go over later. But basically, the most common is when you have two people who are picking the same things from the same pool of things. And I'll go over later. I don't know the bullet points here, but cool. Anyway, moving on to the problem. So we have two cubical die, and they each have removal numbers 1 through 6, and the 12 numbers on the 2 dice are removed, put in the bag, and drawn one at a time and randomly reattached to the face of the cube. 1 number to each face, and then the dice are rolled and the numbers are added. So what's probably the sum is 7. So at first it may seem this problem is really complicated, as you really don't know what number is going to end up on what die and so on. But the cool thing about this problem is that you really don't need to. The part about the dice are really just sort of to throw you off. Why is this? Basically, what you have is you have 12 numbers, 1 through 6, each appearing twice in a bag, and we really just want just to choose 2 numbers from the bag. And this works because of the symmetricity of everything, as you really can't predict what numbers are going to be on what dice, but you can actually, but you know that the probability of any number appearing on the or facing up on a dice is going to be equal. Now, what does that mean? Basically, we just want to choose. Okay, actually, I'm going to claim that the process in this problem where you randomly reattach and then roll it again, this is equivalent to just choosing two numbers from the back. I'm just going to claim that this is the same exact thing. It's the same to roll the two dice as it is just to take two random numbers out of the numbers 1 through 6 and 1 through 6. Combined into like one bag. I hope you can use reasoning for why this is. And once you know this, then the problem becomes pretty easy. There are a few ways to do this. You can either do casework on ways you can choose. For example, that you either choose like a 1 and a 6, or 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1 in order and such. And each one has some number of ways to do it. I think it's just like ways to do it and then so on. But an easier way actually is just to realize that for any number that we choose first, so let n be the number we choose first, the second number will always exist, always as possible as 1 and 6 out of 7, so the extremes will work. So then there are 11 numbers left, and exactly 2 of the 11 will work. Because 7 is odd, so it can be divisible by 2. So if you choose a 6 first, there are 2 1s in the back. If you choose a 5, there are 2 2s, and so on. This means is that you have 2 acceptable cases over 11 not, and then that's your answer, 2 over 11. It seems pretty like simple, but don't overthink it. It is what it is. Okay, well, if this method seems a bit too easy, okay, well, never mind. I'll just move on, and I'll move on. If you have time, we'll come back to this problem if there are more questions. Any questions? Anyway, so our next problem is Bernardo randomly picks 3 distinct numbers from this set, and Sylvia randomly picks 3 numbers from this set, and they arrange them in descending order to form a 3-digit number. So what's probably that Bernardo's number is larger than Sylvia's number. So first thing you realize is that once you pick the 3 numbers, the 3-digit number that they form is fixed. Yes, that is right. Okay, and basically, this problem is a perfect example of exploiting symmetry right here. If there's symmetry, try to exploit it. And why is this? Because we can actually split this problem into 2 cases where Bernardo, he either picks a 9 or he does not. If he picks a 9, then his number was automatically going to be greater than Sylvia's, because hers cannot be greater than, her 100th digit cannot be greater than 8. You'll see later. So all we need to do is find the probability of each of these cases working. So if Bernardo picks a 9, that basically means he has to choose 3 numbers, and 9 has to be one of them. So he has a 3/9 or 1/3 chance of picking a 9. Basically, that's literally just 3 out of 3. He has 3 slots out of 9, and there's a 1% chance that 9 is going to be in. So basically, it's probability picking 9. So for the probability of Bernardo winning or whatever is going to be 1/3 plus the probability that Bernardo has a larger number than Sylvia, but only choosing between the numbers 1 through 8. And here's what I mean by exploiting the symmetry. We know that the chance that Bernardo's number is larger than Sylvia's is going to be the same as the chance that his number is smaller than Sylvia's, because they are all choosing from the same set of numbers, and they're choosing like with the same exact conditions. So that's what I mean by the symmetricity. So all we have to do is find the probability that the numbers to choose are the exact same, and then we subtract that from 1 and divide by 2, and then that's the probability that his number is greater. So basically, there are a total of 8 choose 3 squared ways in which they can each choose a number, and there are 8 choose 3 ways in which the numbers can be the same. So that's actually with the 1/56, and this is the probability that Bernardo and Sylvia choose the same exact number. And I hope you see where I get these numbers from. The denominator is just the total number of ways that they can choose 3 numbers, and this top is that each possible number they can choose is just one case for which they're equal, and there are 8 choose 3 total cases. Right. So now we know that the probability that Bernardo is larger is just going to be 1 minus 1/56 over 2, and that's going to be 55 over 112. And we know that the probability is going to be just this. And we multiply this by 2/3 because there's a 2/3 chance that he does not choose a 9, and we need that to happen. So we need him not to have a 9 and for his number to be larger, which is why I multiplied the extra 2/3. So what we're left is 1/3 plus 55 over whatever this is, 168. And this is equal to 56 plus 55 over 168, or 111 over 168. And they're all divisible by 3, so we can divide by 3 to get 37 over 56. So yeah, cool symmetry problem. Moving on. If we have 20 boxes in a line, and each of them contain 1 red marble and K white marbles, and Isabella begins the first box and just keeps on drawing marbles until she gets the red one, what was the probability that she stops after drawing exactly n marbles? And this probably is less than 1 over 2010. What you do this problem is you look for a pattern, or you can just simply find a general formula. So basically, we can think about what this problem is asking. So the first box is going to have one white and 1 red. The second box is going to have 2 white and 1 red. Next one is the third, 3 and 1, and so on until and whatever. So you get 1 white and an increasing amount of 1 red and increasing amount of white. So the probability that she stops after drawing exactly n and gets her first red, that must mean that for the first n-1 boxes, they were all white. That happens with a probability of 1/2, 2/3, 3/4, and so on, all the way to n-1 over n. And then in the nth box, which has n white and 1 red, she chooses the white one, which happens with probability 1 over n plus 1. Am I right? Yes. Basically, this is going to be equal to P of n, and we can actually cancel out the denominator of a fraction with the numerator of the fraction right after it, as basically it's just you add 1. You basically add 1 to the top and bottom, so it works out that way. Until eventually you're just going to get this equal to 1 over n times n plus 1. And from there, you just need to find n, the smallest n, such that n times n plus 1 is greater than 2010. And this would happen when n equals to 45 is going to be the smallest one. And basically, the method, which is actually an algebraic method that this problem used, is called telescoping. If you guys want to learn more about it, it's called telescoping. And it basically just takes really long series of you basically take a really long series of multiplications or additions or anything like that, and you cancel out the entire middle of it, so you don't have to worry about the beginning and ending terms. Yes, very, very cool method that you might want to look into. So yeah. Moving on. This problem. So basically we have a 3 by 3 square, and it's partitioned into 9 unit squares, and each of the squares is either white or black. And now after we rotate it 90 degrees clockwise, we want to see the probability that it's entirely black. If a white square is in a place that was black, then it becomes black. And if the black square, then the black one just stays black. So yeah. And first you want to figure out what this 90-degree rotation means. And that simply means that if we label these 1, 2, 3, 4, 5, 6, 7, 8, 9, then we're just going to be left with something that looks like this, where we have 1, 2, 3, I believe the 5 stays here at least. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is what the rotation would sort of do. So basically what you notice is that the center stays the same. The numbers in the corners are going to be shifted, but they stay the same, and same with the edges. So we really have 3 separate things we need to focus on: the center, the edges, and the corners. I have not. Basically, the center has to be black, and this happens 1/2 of the time. And basically, if it's not black, then the center is just going to stay white, and that's not going to solve the problem. The edges, okay, and now the edges and if you notice edges and corners, the cases are actually going to be identical. And basically, you notice that 2 and 8 and 4 and 6, for example, they're always going to be opposite of each other, which means that at least one of the sets, 2 and 8 and 4 and 6, they must be black, because both numbers are black. And this can basically happen if we do cases. If 2 and 8 is black, then we have either 4 is black, 6 is black, or none of them are black, or both of them are black. So basically, this can happen in 4 ways. And symmetrically speaking, if we consider where both 4 and 6 are black and 2 and 8 are both white, or one of them is black, one of them is white, or they're both black, that's another 4. And we subtract the one case where they were all black that we overcounted. That can happen 7 ways. And the same for corners. Since there are 4 edges and 4 corners, then we have to divide each of these by 2 to the 4th, which equals 16. So the probability that they're going to be what we want is 7 out of 16. Then we can just multiply them together and get 49 over 512 as our answer. Voila. Anyway, this is really just a counting problem inside a probability problem. That's really it. You do casework and basically solves the problem. I might be rushing a little bit, but we still have a few more problems to get through. Anyway, suppose, this is one of my favorite ones. Suppose that one of every 500 people is in the certain population has this disease, and it has no symptoms, and I'll let you read it. This is sort of interesting. And basically, there's a 2% false positive rate, and which means that 90% of the time it will turn out negative if they're negative, but 2% of the time they'll turn out to be testing positive for the disease without actually having it. So you want to find the probability that the person who is chosen at random and gets a positive result actually has the disease. And yeah, it says which one is closest to. I should have changed that, but it's actually going to be. But if you had the answer choices, you'd actually be able to tell pretty easily. So I'll go into that when we get to the problem solving varieties. So when we approach this kind of problem, we have to realize that this information is actually useful. That we actually sort of need to know that how common the disease actually is. If we only work off of this part where 2% false positive rate, then obviously we'll know that this positive test result, we actually won't be able to tell. Okay, sorry. If we don't know the probability that the disease occurs in, then given only the false positive rate, we actually will not be able to figure out the actual probability. So yes. Anyway, the way you can do this problem is just simply consider if we have 500 people. We know that one of them is going to be positive. Everyone is going to be negative. So in the 499 negative tests remaining, 2% of them are going to be a false positive. And 2% of 499, which is going to be 150th, is around 10. It's like really close to 10. So around 10 false positives. So that means that the probability that there's a positive, that the person is actually positive, is going to be 1 over 11. As there's only one person who's testing positive, well, 10 of them are false positives, and we're only considering people who have tested positive. So there's only 11 total people that this could be, and only one of them is actually going to be a positive test. So P is going to be closest to 1/11. And this actually sort of seems counterintuitive because, well, you'd assume that with such a high success rate that this would be able to more accurately pinpoint someone with disease, but in reality, you have to be careful. This is called the false positive paradox. It's a cool thing that you can look into later. It doesn't really have much to do with like the actual math here, but it's an interesting thing that can work. So yeah, look this up. It's cool. So yeah, the answer is 1/11. It seems sort of small, but it's the answer. Next one. Chloe chooses a real number, uniformly random from 0 to 2017, and Laurent chooses from 0 to 4034. What is the probability that her number is greater than Chloe's number? And this is really just a very obvious geometric probability problem. And if you have Laurent's number equals to x and Chloe's equals to y, then we can just sort of graph it. X and y are like so. And basically the total number of points that we're considering is just this rectangle right here. And we want the number of points such that x is greater than y, or y is less than x. So it's just if we graph the line y equals x and take everything below it, like here. This point passes to 27. This is 2017. which means that this is exactly the halfway point of the rectangle. So this is gonna be 3/4 as our answer. This is 1/2, and this is 1/2 times 1/2. So yeah, good problem. And yes, casework should work too. I'd assume your cases would be if Laurent's number was between 2017 and 4034, or if it was between 0 and 2017, right? That's what I'd assume you'd do cases on. Yes, another question. I had gotten a perfect score in the AMCA. Yes. Although it was not in my 8th grade year. That's not relevant. Anyway. No, I actually got it in 6th grade. And then my 7th and 8th, two mistakes, bad mistakes, and didn't get a perfect score, but that's fine. Anyway, next problem. Amelia has a coin that lands heads with probability 1/3, and Blaine, or A and B, has a coin that lands probability 2/5, and they alternate their coin toss until someone gets a head. And what is the probability that Amelia wins? This is literally just very obvious geometric series or recursion problem. So you can do whatever way you want, but I'm just going to do the recursion since I think it's a bit faster to write down. The probability Amelia wins is the probability that she wins in the very first round, which is just 1/3, and the probability that no one wins in the first round, it goes back to her turn again, and that happens with probability of 2/3 times 3/5 times p. So we just have 3/5 of p is going to be equal to 1/3. So p is just 5/9. So the difference is just 4. So yeah. Yes, ask away. Well, I don't think you guys should read much into the number on the problems. It's just that I just find them interesting problems, I guess. I don't focus too much on where they're ranked, on how I judge them at the end. Okay, this is actually, I'm just going to skip this one as I think it might be a bit of an easier problem. As if you were judging cell number 11. And all this really tests you on is how well you can count. And but probably, and you can realize 6 or 7 in the bottom reflects the total number of ways this works. So you just have to count the number of ways in which you can have the sum of numbers be 10. And I'm just going to go and say this is just 84. So yeah. So yeah, if you want to do this problem, just see what happens. But anyway, I want to just go to challenge problem as well. Let's write 2. Real numbers x and y are chosen independently and uniformly at random from the interval 0 and 1, with the probability that x, y, and 1 are sidelines of an obtuse triangle. And I'm not going to solve this one for right now, but basically, hints. A few hints. This is a geometric probability problem, as you can probably tell. And we also have some restrictions. You have the triangle inequality. We have Pythagorean inequality. And we also know that 1 is the longest sideline. Because x and y are both between 0 and 1. Yes. Anyway, we know the Pythagorean inequality. This might be the one thing that you guys aren't familiar with. And it's basically if you have side lengths A, B, and C of a triangle, where C is the largest side length, then if A squared plus B squared is greater than C squared, this is acute. A squared plus B squared equals C squared is right. And A squared plus B squared is less than C squared, means it's obtuse. So yeah, that's well, I've gotten a lot of answers. Well, I mean, if you're trying to answer a challenge problem, no one has the right answer so far. I think we're ending in a few minutes. I'm not gonna go further. But yes, 84 is the correct answer for this problem. If you're wondering, I have it written. So yeah, 145 or 147, that's not right for any of the problems. Nani? I'm honestly not sure what you're even talking. Okay, well, guys, class is over. You can leave if you want. I already given out the hints for the challenge problem. So yeah, if you don't want to stay and talk, I guess, then you can leave. Anyway, I don't know what you're referring to by 13 though, because yeah, what's 13 supposed to mean? This is the challenge. Bye guys. See ya. Anyway, the challenge problem is asking for a probability, so it can't be greater than 1. Anyway, I'll let you guys think about it, and I'll post a solution to it later. So yeah, thank you guys for attending class, I guess.